The scientific revolution starts now.
The is the Sci Podcast.
Let us see in the dark.
Today we have a conversation with solar physicist Valentina Zharkova, and our conversation is, for the most part, about the effect of the sun on climate change. We've talked about climate change a lot on this podcast already. We've presented people who are like, it's definitely happening. We've presented people who are like, I don't know if this is something that we need to be worried about immediately. And Dr. Zharkova actually falls kind of somewhere in the middle, because she's like, climate change is happening. It's probably happening in the direction of it getting colder rather than hotter. And she justifies it by her study of the distance between the sun and the Earth, where as the planet alignments change, there's a 2,000-year cycle that pulls the sun away from the barycenter of the solar system, bringing it closer to Earth or farther away from Earth, which has an effect on temperatures on the planet.
And apparently on the temperatures of other planets as well. So climate change isn't just an earthbound phenomena, it's happening everywhere.
Which would make a lot of sense. So this is a deeply intuitive way of looking at the solar system and recognizing that there are multiple ways that the sun interacts with the planets, and that's going to change what's happening on those planets. So that's great. At some point in the conversation, though, it goes a little bit haywire.
Yeah, we turned our attention to some of her earlier work, which was about these seismic ripples and the seismicity of the sun. And Zharkova was looking at it as a sort of liquid-like process, which of course brought up one of our favorite interests, which is the liquid model of the sun. And in particular, when we tried to talk about the blackbody spectrum of the sun, things kind of went off the rails a little bit. And so we decided to cut the conversation there because nothing really productive happened after a certain point. But I want people to have a tiny bit of context with regard to the idea of the blackbody sun. And so the best way to do that would be to go back to some of the podcasts we've had where we really get into the nitty-gritties of this. The most recent conversation was with the liquid plasma physicist Patrick Van Reyes. That's DSPod 190. Before that, we talked with Dr. Alexander Unziker. That was podcast 163, where he lays out essentially a liquid model of the sun that goes back to the work of Dr. Pierre-Marie Robitaille. Dr. Robitaille has his own channel dedicated to all the details of this called Sky Scholar here on YouTube, which you can go and check out. And we also made this short little video to summarize the basic principles.
And we also have 4 conversations with Pierre-Marie on the show from back when we were puppets. So it's like early in the days. I don't know the episode numbers, but if you go back far enough, you'll find them.
But if you want to understand going into this why it's such an emotionally fraught subject, you basically need to understand one thing. When you look at the light that's emitted from a gas in a laboratory, you see these nice little bands of light emitted, discrete frequencies. This is just an empirical fact. When you heat up a solid or a liquid, you see this very beautiful rainbow of light, all these different frequencies, and they have a particular shape to the power, the intensity of the light from each one of those frequencies. That shape is called blackbody radiation. And in fact, the radiation that we see coming from the surface of the sun, the photosphere, is very, very close to a perfect blackbody. Of course, there's the atmosphere, which has gas absorption lines and so forth as well, the corona area. And so the treatment of the sun as a gaseous plasma, in fact, counts in astrophysics as the one example in the universe where gases are able to generate this spectrum, even though we can't do that on Earth. And as a result of that, cosmologists are able to say that the gaseous plasma at the beginning of the universe gives the black body spectrum of the cosmic microwave background. And so the cosmic microwave background is proof of this Big Bang business. So you can see that it's at the heart of so much of astrophysics, so much of cosmology, and it's a really, really interesting contradictory piece of evidence. That's why I think the conversation heated up to the point that we actually kind of had to shut things down.
But hopefully we will have Dr. Zharkova back to talk in greater detail about the continuous spectrum and the blackbody spectrum, because there's clearly a lot still left to discuss, and we're trying to work out the context of what that conversation would look like by email right now. And so for now, enjoy the conversation about solar barycenter shifts and climate change, and we'll come back next time and talk about blackbody radiation on the sun.
Good morning to you, while it is good afternoon in England.
Yes, you must forgive me. I'm just waking up. This is very early for us. We have to get up at 6 to make this happen.
This is why I said good morning to you.
Yeah, so we've had a number of conversations. We're starting to investigate climate. We've talked to, Richard Lindzen, Gavin Schmidt, who was
Nir
this?
Shaviv.
Nir Shaviv.
Catherine Richardson.
Catherine Richardson, that's what I was thinking of. We recorded with her last week. We haven't released that conversation yet. But it's very, very interesting to me how very different everybody's perspective on the data is. Let's put it that way. The way that people interpret the data. And actually, I think that's really exciting because my favorite part of science is that interpretive level where you look at all of the data on the table and you try to piece together, string together what's happening, fill in all of the missing pieces of the movie and explain it, really, give the cause of the effect. And so I'm really excited to add your perspective because I know that you are considering our star and how that affects life here on Earth, particularly climate. And that's something we haven't really cracked open much since we first met with, I believe it was the director of the NASA heliophysics program.
Nikki Fox.
And then Laika.
Madhulika Guhatakurta.
Is she the director or is she...
Lika runs the Living with a Star initiative, and then Nikki Fox is the director of the Parker Solar Probe program.
Okay. But Madhulika said that NASA was going to start holding symposiums to consider how the sun was affecting Earth, as in so much as climate, also in so much as seismicity, which is really interesting, storm formation, things like this. And so we're going to have her back on the show in the next month or two and try to see where they're at with that. I know they were going to have a big symposium. I believe it was over the summer. Could have been last year. This has been a while. So anyways, it's a really, really, really exciting topic to us. And I guess it'd be a great place to begin by understanding what brought you into this topic. What's your own personal story to studying climate and studying the sun? Like, how did you get to that?
Well, I got to studying the sun after the university because I graduated from applied mathematics, and part of our applied mathematics was astronomy and physics. So I started investigating the sun and did my PhD in astrophysics in main astronomical observatory in Ukraine, in Kyiv. So this was my main topic. I did PhD in radiative transfer, which is a very important mathematical topic, and explain emission of filamentary prominences in the sun. So most of my life, I basically was investigating emission and energetic particles on the sun. So I do a lot of plasma physics related to solar plasma, particle acceleration, particle precipitation, emission, hard X-ray, soft X-ray, UV emission, optical emission related to flares. And I also discovered and we explained how the sunquakes are produced. Similar like we have earthquake, we have on the sun sunquakes, and we discovered them in 1998. It was big news in all channels in all 5 continents. And since then, so this is my main topic, was investigation of solar activity, but mainly through the particular event, active regions or solar flares or filaments. So how did I come to general solar activity? It is a very interesting topic, which came absolutely unexpectedly. When I got my lectureship at the university, I got one grant was on plasma physics, investigate what I normally investigate, energetic particles and their emission, on which I wrote a couple of books and many papers. And another came as a European grant, European grid of solar observations, this project was. And we were taken the responsibility to detect on solar images all the active features, sunspot, active regions, and automatically with the tools of image processing. So this is how I got to image processing. I was the leader of this working group. So we developed very nice automated tools. We published a book explaining how we done it. You can find it on the website, published in 2007.
Where was this at, by the way?
Huh?
Where was this all taking place?
It was taken in the United Kingdom, University of Bradford. At that time I was working. And you can find on my personal webpage, solargsm.com, I listed all the books which I edited and contributed. So one of the book called Artificial Intelligence in Astrophysical Images or something like that. So this what we done. So we processed for the whole solar cycles a number of sunspots, I think about 150,000 of sunspots, normal features, and then active regions, and then filaments. And we built relational database, if it means anything. It means relational, it means that anyone can do the searches. So in our database, each detected features has, for example, 20 parameters, density, magnitude, magnetic field, shape, size, location. So by any of those parameters, you can do the search and see how many of those were in the whole cycle or in the particular period. So we built this database. When the project finished, it was 2005. We had this beautiful database which was published, and the grant was finished. So I am very consequent scientist. I cannot leave job half complete. I thought if we done the database, we need to analyze it. So I thought nobody else knows our database better than us. So let's do statistical analysis. This is what started all this investigation in general solar activity, because all these features are those which represent solar activity in general. Sunspots, active regions, filaments, and coronal mass ejection. So this is how we started our first statistical analysis, 2005, 2006, 2008. What we were planning to do, the solar activity index produced by software. So we thought we are so smart, we can produce solar activity index, average sunspot number, by making a program. It turned out it is not that simple, because how they produce it, they rely on the experience of the observers in each observatory, which has very personal experience, which you do not know how to emulate in computer science. So eventually I realized that we cannot produce actually automated index of solar activity with sunspots. But by that time, we did a paper in 2008, Zharkova et al., where we discovered that actually sunspots are following the variations of the general background magnetic field. This is background magnetic field which allows sunspots, first of all, appear on the surface. It indicates in which part of the surface sunspot could appear. And this magnetic field also shows to the sunspot when they need to migrate toward the equator, as they normally do during the solar cycle. So when we discovered that actually background magnetic field has an upper hand, and it much better represented data, because we have 1024 by 1024 pixels of background magnetic field instead of tiny number of those sunspots sitting on the disk, which is somewhere 100th part of the solar disk, gives a huge error. This is why we couldn't do any automated different classification. So we thought, okay, let's come back to the good guy mover, that they measured this magnetic field for the past 3 solar cycles. We started this in cycle 23. So cycle 21, 22, 23, they all been measured magnetic field from 1976. So we use the data. Wilcox Solar Observatory, low resolution data, and try to see behavior of background magnetic field.
And how are you looking at the magnetic field? Are you looking at polarization of light, or what? How are you doing that?
Magnetic field is measured obviously from Zeeman polarization. So this is how people done in observatories. So they use a Zeeman effect. They use various elements, spectral lines. For Wilcox, they use, I think, it was not iron. It was other line. I've forgotten which line it is, but it's still Zeeman effect because the magnetic field is big. But what we are not calibrating, we taking what the observatory gives us. What we got a big set of magnetic field. From the pole north to the south, from the east to the west, huge amount. There's 1024 by 1024 pixel, and all this magnetic field because magnetogram measure on the magnetic field. So we needed to classify somehow what we got. So you get this huge data. It is like you look at the white light and think, what kind of wavelength is in this light? So we, obviously mathematicians, we know what kind of wavelengths are in the white light, and we know how to detect it. We know the diffraction effect. So if you put your white light onto glass prism, this white light, because of different diffraction law, immediately split into the rainbow from red to indigo line. So seven definite wavelengths will be appeared. So this is glass prism is very important thing which decode white light which doesn't have any wavelength because it all mixed, everything in disorder, immediately put into the different wavelengths with very nice order. So we wanted to find similar thing which works for magnetic field. And we discovered that the best thing is to do this is principal component analysis. It allows you to detect, to separate from the vast majority of data, separate threads or separate events or separate waves, similar like prism does to wavelengths of the white light. So this is why we use principal component analysis, and we obtained eigenvalues for vectors of magnetic field. So we have every day we use the 15 north and 15 south strips for magnetic field. We average this magnetic field along the longitude, and we look on the latitudinal distribution, and we look its development over the time. Therefore, we have these data. We managed to discover eigenvalue and eigenvectors, which shown us that they came in pairs. So these magnetic waves, which we managed to separate from the total summation of magnetic waves in the magnetograms, in the data, raw data, we managed to separate actually quite a number of waves, more than the 30 different, but the most prominent were the first 8 eigenvectors, and they came in pairs. What was surprise, no one knew that, no one suspected, but these eigenvectors, magnetic waves which sun generates, came in pairs. The biggest pair, we call them principal components, they have covered by variance, eigenvalues were defined by variance of the data responsible for this particular set of wave. So it was 19 and 20%, 39% in total in variance. If you convert variance, it is square of standard deviation. So if you go square root
I think we might be giving people a heart attack with the word eigenvalue, but I think what we're really talking about is determining the shape of these magnetic
absolute oscillations. Let me explain eigenvalue to you. If you look in the Google, you look at Tacoma Bridge. Tacoma Bridge
Gallop and
which
Gertie.
was destroyed by the wind. So what I'm trying to explain, that each system, whatever it's built, it has its own natural frequency. Natural frequency is defined by these eigenvectors, eigenvalues. This is the frequency of the waves which the system produces, its natural frequency. So when they built Tacoma Bridge in the United States above this big canyon, they've forgotten that this bridge will have this eigenvalues or natural frequency because of big gales. And exactly this what happened once the gale of 50 miles per hour started blowing, and this bridge built from metal and concrete started waving like it been done from a paper. So therefore, the forcing force from the gale coincided with the natural frequency of this system with this eigenvector, and caused bridge actually destroyed bridge. Bridge completely was broken. The similar happened in the Millennium Bridge in London when they built the bridge. You know, Millennium Bridge. You can walk through Thames River, but it is a bit wavy. And when people started walking, it turned out that natural frequency of this bridge, torsional oscillation, was equal actually to the speed of people walking on it. And bridge started waving. Luckily, someone was smart. They immediately removed people. It took a whole year to restore some resistance that to avoid this resonance. So this is what I'm saying. Eigenvector defines the natural frequency of the system. So what we define natural frequency of the solar oscillation, of the solar dynamo. Not added together like in the whole magnetic field. We define each split, each component, like red line. Let's say that now we define it indigo components, the strongest one. And
it sounds like you're saying that there's a complex harmonic of the solar dynamo, and you were able to decompose all of the frequencies in that complex wavelength,
like a Fourier transform or something.
It is not Fourier. It is principal components. But if Fourier helps you to understand, these are harmonics. These are not exactly harmonics. These are the waves produced by different magnetic sources. So these biggest two are produced by dipole sources, north and south. Mm-hmm. We have another two beneath with the smaller eigenvalue, which are produced by quadruple sources. So you have 4 sources. And then we have another produced by sextuple sources. And the last biggest one produced by octuple sources. So this is how magnetic field is produced in the sun.
Hey guys, if you're sitting there thinking, how can I make this podcast even better? Well, you can come over to patreon.com and join our inner crew, meet with us once a week face-to-face, and plot out what we can do to find better guests, to host better interviews, and you can help us keep the lights on over here. We also have our first conference coming up April 7th and 8th to coincide with the solar eclipse in Austin, Texas. And we're going to have some incredible speakers there, and it's going to be a small crew so you can actually spend time with us, spend time with the speakers, and get some real contribution to the discussion going. We'd love to see you there. If you can't come that weekend, if you don't have the money to become a patron right now, that's fine. Just share the episode with somebody, or maybe you know somebody, or maybe you yourself has some skills that you can contribute. You know, we could really use a new logo around here. We could really use some design help. We could use help with animations. Whatever it is that you do, reach out to us and tell us how you want to get involved. It would be really, really useful. And now back to the conversation.
So we managed to detect inner frequencies, inner waves of the solar dynamo, which helps us actually to interpret our data, because now for these biggest vectors, principal component, all dynamo theory start working perfectly well because it's been developed for dipole sources. So it's been developed for dipole sources, but the whole magnetic field includes all of these components. Now we gave dipole sources. You wanted them, please take them. Here they are. Not only we derive them with principal component, we manage to describe them with the series of 5 cosine functions analytically. So each component has analytical formula. So you can only change the time and calculate how this component changes now in 1,000 years forward, in 100,000 years backwards. You just need computer time, nothing else. This is how we arrived there. And when we arrived, we thought, we managed to give them formula. So now people will be very happy because you can calculate the solar activity. And we reported this paper in 2015 at National Astronomy Meeting in London. It was on the press release news, Royal Astronomical Society. So we discovered that this is the first time we discovered that we not only have 11-year cycle, but we have also 330 or 380-year cycle, grand solar cycle. And we were about to enter to grand solar minimum. This is what we reported in London. And this is how I got into the climate, because as soon as we reported this from the point of view of solar physics, I didn't do climate at all before that. Before 2015, I did pure solar physics or pattern recognition or artificial intelligence. But as you know, my background in mathematics very strong. So when we arrived there, we reported, and suddenly all the journalists pick up, said, it's grand solar minimum, it will be like Mount the minimum, it will be cold. So suddenly it occurred to us that we not only discovered something in solar physics, we discovered something which affects actually the whole Earth. Because indeed, if we are entering into the grand solar minimum, it is a unique situation. You have the front row to observe this grand solar minimum, which will be similar like Mount the minimum in the 17th century. Just take your popcorn and good heating into your house and maybe food and watch it or survive it. You need to survive it. So this is when everything started, because this is how we got into the radar of the people who do climate. They were not very happy at all that this grand solar minimum coming. They said, no, it will never come. It will never come. There were no grand solar minimum because their models cannot explain grand solar minimum during Mount the minimum. The models are very unflexible and not explaining many effects. So they realize if we are having now grand solar minimum and we're entering, it is a big strike to their model validity. This is
well, they often, it seems like they report that that the Earth is getting warmer, right? I guess they've kind of backed off that a little bit lately, but it seems like that was there's still the global warming narrative that most people understand on the street, right? That the Earth has increased its average temperature by, I don't know what, half a degree or something?
Anywhere between 0.5 and 1.5, yeah.
Right, since the 70s.
But this is a different kind of effect. So you imagine that Sun is in the center of solar system, planets are flying around, and Earth is sitting on the orbit. And Earth has inclination towards the ecliptics, and it changes the climate. Within 100,000 years, we had this ice period, 100,000, when everything ice out, is because the Earth is turned around away. So this is called Milankovitch cycles. But there are other cycles which affect. So you have heating coming from the sun defined by solar dynamo by itself, but also the heating can come from the sun defined by the orbital position of the Earth and the sun. And this global warming, we later did paper in 2019. We calculated this solar activity magnetic field eigenvector for 120,000 years backwards. This is what we done. And we discovered that the zero line of magnetic field, so if magnetic field increases during cycle to this north to the south, zero line should be zero, should be straight line. What we discovered, the zero line has tiny, tiny oscillations, which are very, very periodic, very strictly periodic oscillations, which gave us a clue that the sun is not sitting in the focus of the elliptic orbit, as it's supposed to be by Kepler law, but it fluctuates around this barycenter of solar system, and it calls solar inertial motion. It fluctuates under the gravity of large planets. So Kepler law explains how the planets are moving around the sun owing to the gravity of the sun. But after Kepler discovered that law, about 20 years later, Newton discovered the gravity law. Kepler did not know about gravity law at that time. So later on, in 1965, one author calculated the effect of large planets and discovered that these large planets drag the sun from this center of ellipse towards the part of the planetary orbit. So, for example, in this millennium, it drags the sun towards the point of spring equinox in March. So the sun becomes closer to the Earth orbit from February until August, and with every year become closer and closer. This period when become closer is about 1,000 years. So it started moving towards this point at the end of Mount the Minimum. This is when last maximum was, and it moving now closer to the planet Earth and other planets. This why it is temperature is increasing, especially it increases in March and July and not in the winter month, because the sun is closer to us. And it will be increasing until 2,600 years. This will be another 1,000 years, it increasing from 1,600 to 26. And then after 26, it start moving back again, decreasing to the level like it was during Mount the Minimum. This is so-called Halstatt cycle. It was well-known cycle. They never linked to the nature. They measured this cycle from the abundance of carbon-14 and beryllium-10 isotopes in the biomass of the Earth. And they discovered they have every 2,300, 2,200 years, they have variation of increase of this biomass. So radiation from sun become bigger and then decrease of it. So suddenly now we, in that paper, we suggested that probably because the sun moved closer to the Earth, then its radiation doesn't matter on which stage of solar dynamo it is. Its radiation puts more because the distance between Earth and sun decreases, right? Because it moved from the focus, it becomes closer to the Earth. This is why we have this global heating. But
can I ask you really quickly? Is the barycenter drift primarily due to the giant planets?
Yes, it is from Jupiter, Saturn, Uranus,
and
Neptune.
Their orbits. How long are their orbits? Do you know off the top of your head? Very long, right?
They're long orbits, and this is why they induce this wobbling for about 2,100, 2,200 for the sun. So the sun is wobbling around the barycenter of about 2 millennia.
Is that because it needs to?
We calculated this oscillation to 120,000 years ago, and we discovered that the Earth had this fluctuation 62 or something to 120,000 years before. So definitely the Earth can easily survive this increase of the temperature.
Hold on. I still don't understand how. Can you tell me the length of the orbit of Jupiter, the period of Jupiter? Does anybody know
the length of orbit? I think the results,
I can look it up.
It's not like a million. It's not hundreds of thousands of years, though, right?
From Jupiter, from people who did celestial mechanics. I'm not celestial mechanics.
What's your question here?
Yeah,
Kuznetsova Perminov. we use their simulations. If
Like,
you're interested,
I'm trying to understand
you can interview them.
how a short period, like relatively short
It's about
period.
12
They have
years.
short
Okay, it's
periods
about-
as well. They
I'm
have
sh-
periods 176 and 360 years. They have these periods, and been known from 1965 until now. It will well recorded. The inertial motion of the star is at the bottom. How astrophysicists look for exoplanets. They look for the star which has wobbling luminosity.
Yeah, I
As soon as
understand.
they
I
see
understand
the
that.
star has wobbling luminosity, they know that the star should have a planetary system.
Yeah, I totally understand. I'm just trying to. I'm trying to understand.
Must have similar like Earth planet.
I'm trying to understand how a short periods can sum to large periods. Do we need to have like this alignment, this syzygy between the different gas
Yes,
giants?
they have different alignments because the interference between different planets. They stand in different positions, and this is why this guy calculated all the celestial mechanics. You look, Perminov and Kuznetsov, I cited them in our paper, in my book as well. So you can see how they calculate. I am not celestial mechanics person. I use what people do specialists, but definitely these the gravitational force from the planets move the sun, because the sun distance, why I know this, I'm not calculating anything. I take sun earth distances from official ephemeris of NASA, from JPL, and from Paris Meudon Observatory. They have sites. I compared them. They exactly to 7 digits, the same. So I use them and I calculated these distances, and I proven these distances do change. So those people who claim that the distances do not change, they did not do the homework, because the ephemeris are officially available. Anyone can download them, and anyone can see that the distances change. In my book chapter, which you can find in the publication in solargsm.com, you can see the appendices, which plot variations of distances and corresponding variations of solar irradiance.
It makes
Okay.
sense from first principles that they should change. Like you said, that's how we detect these exoplanets in some cases and so forth. Of course, they should change just by basic Newtonian mechanics. I guess I was just trying to unpack how it is that you get these larger cycles out of these smaller
they
cycles.
did not.
Well,
When
you
we
have-
publish
Oh, well,
only,
hold on. You have compound cycles here, right? Because you have multiple planets that are large and aligning. And as you align more and more of them on one side of the sun, that period is not the same period as the orbital period of a single planet. And so you basically have, an 11-year cycle for Jupiter, but then the cycle for Jupiter and Saturn conjunction is like 800 years for their maximal conjunction.
Because Saturn's is like 30 years or something.
Well, it's an oscillatory system, and they're not timed to one another, and so it's like the same way. It's like when you're sitting at the stoplight and you've got your turn signal going, and it like periodically syncs up with the music that's playing, but then it comes back out of phase. It's the same sort of thing, like except on a planetary scale, and so it takes much longer.
Got
And
it.
so-
I just wanted to unpack that for people who are listening.
The period was, what was the period of these oscillations? 2,600 years?
no. The period is 2,100, 2,300 years.
Okay.
It's a Halstatt period. Halstatt. Halstatt.
Halstatt,
Well-known period. It's been recorded and reported for.
yeah,
for decades.
we're this is not an argument. This is us just trying to like to just lay out the various mechanics. Halstatt has come up before because do you know about the Halstatt plateau in radiocarbon dating?
Pardon?
So there's this thing called the Halstatt plateau in radiocarbon dating, where there's this period. So if you look at the at the carbon-14 signal over a long period of time in a radiocarbon dating system, there's a linear decay of your radioactive.
Well before current cycles, we did frequency analysis in our paper published this year, periodicities, and we found using the solar radiation data by Steinhalber and by other guy from Max Planck Institution, and we derived the period 2240 and 2300, which coincide with the period we defined with the magnetic field zero line oscillation 2100. So this more or less coincide with what people observe from these particular abundances of carbon-14 and beryllium-10.
Well, because there's a weird flat period in that graph.
In million years, not in 1,000 years. We're speaking about smaller period. It is, we need to move on somewhere where it's not in our period. So I'm not speaking about million years. I'm speaking about a few thousand years. Maximum Holocene, it is 12,000 years. This is what we considered. So and we don't have Plato in 12,000 years.
So this is crazy. So the Halstatt plateau is that radiocarbon dates of 2,400 years ago will always calibrate to about 800 BC, no matter the measurement precision. There's this there's supposed to be a linear relationship between, and this is you mentioned Halstatt.
I'm not measuring what they do in.
I'm not saying you do. I'm not saying you do.
I calculated the frequencies from their measurements. Obviously, this plateau was there, but frequency wavelet analysis did not detect it. So we detected with wavelet analysis, and I'm not discussing it anymore. Okay?
You mentioned the guy named Halstatt, and I was like, I'd heard his name before in a completely unrelated.
Yeah, you heard from something, and it is not related to what I'm saying. It is different. I'm speaking about 2,000 year period, 2,000, not 100 or 10,000 or whatever.
Yeah. I was just surprised that the Halstatt guy came up again. But let's see.
You're a great specialist. Yeah, I allow you to express what you're surprised and what you say. I did not look at the particular plateau, and I'm not interested in it. I was only interested to link variations of the solar irradiance with the variations of magnetic field, and I found this correlation that this is approximately 2,000 years, 2,100, 2,300, which explains why it is happening. And it can be happening only because the sun moves from the center or barycenter of the solar system towards the planetary orbit.
So here's a question. Do you think that it would be possible to look at the other atmospheres of planets and track heating in them due to this barycenter change?
Of course, people look already. When we had melting ice on Earth, the ice was melting on Mars, but your people from NASA they just failed to report it. And similar, we have Jupiter have typhoons during the increase in temperature. It increasing in Jupiter as well. It never had typhoon before in previous 300 years, started having now. So if someone did proper investigation, they would probably report. I found this publicly available, but they just forget to mention it. So each planet is affected. Each planet.
That's really, really interesting.
Specific planet.
Yeah. I mean, I think that kind of planetary solar system analysis is really interesting. But I remember there was a big kerfuffle when you published this paper, right? You published it in Nature, and then there was a campaign to get it retracted. And
yes.
there was, and then later, I think that when we were talking earlier, you said the campaign to get it retracted was on the basis that you had made this analysis on your paper on the assumption that the barycenter was changing, but you didn't.
I did not make analysis in that paper of solar irradiance. I did only evaluation in 7 lines in the last section and said, if my zero line fluctuates, then the distance should change. And I look how it should change from solar inertial motion. They say it should change to about the whole solar radius, solar diameter. So your sun can move at the distance of solar diameter from the ellipse. So I evaluated, let it move on solar diameter to the south and let it move to the solar diameter to the north. This is it, nothing else at that time, because I didn't have time to look at the ephemeris and I didn't realize it will be so critical for them. Indeed, they produced, paper was published in July, and they produced campaign just bullying us and behaving absolutely disgusting. So eventually they made the editor to retract our paper on the 5th of March 2020 on the basis that the Sun-Earth distance cannot change this much. Maximum, I said that Sun-Earth distance was changed by 0.16,000 astronomical unit per 2 millennia. But they said it cannot be, and we had great specialists, Ken Rice, saying, pretending he's a celestial mechanics specialist, saying, no, the Earth moving with the Sun. So the Sun has this inertial motion, but the Earth moving with the Sun like a dog with the owner. So it was 5th of March, 2020. 23rd of March, we got into the lockdown. They put us at home. You sit at home doing nothing. This is when I decided, why don't I look at the ephemeris? If they say that the sun distance doesn't change, the ephemeris should show.
What are you've mentioned the ephemerides? The ephemerides? What are these?
Pardon?
This word that you're using, ephemerides. I've never heard it.
Ephemeris.
Ephemeris.
It's a calculation of position of the sun and the Earth on the sky. You don't know that every time, every planetary body can be calculated where it is related, where it is on the Earth, including influences of multi-bodies. So they do it officially in NASA. They have specific code, and this position they call ephemeris. So they officially published on the websites, and I downloaded them. First downloaded from Paris Medon, then I downloaded from NASA, checked if they are different. No, they have coincidence on 7 digits after comma, so they're absolutely identical. And this is what started building distances from 600, then 1100, then 1600, then 1700, 2020, and 2600. So this for 6-7 years, I downloaded distances between Sun and Earth, and I proven in plots these distances indeed change from with 0.016,000 astronomical unit within 2,000 years. So my guess was absolutely correct. After that, I wrote to the editor of the Nature, demanding that they withdraw this retraction of our paper and send us apologies. He refused. He said, "Oh, you can publish new papers." So they done this just to help these guys who cheat the whole humankind with what they say global warming. Global warming comes not from the planetary effect; it comes from the sun. So I wrote a letter to the publisher Springer, and they said, "Oh, we do not get into the decision of the editors. So it is like complete irresponsibility." I also wrote to the Vice Chancellor of Edinburgh University, where the specialist Ken Rice works. If he pretended to be specialist in celestial mechanics, you could ask him where the Neptune and Jupiter affect this, because he was claiming in this discussion when they bullied my paper on the website. They said this distance doesn't change. I have all the proof in Discuss. They put his plots. He plot distance. So I wrote to the Vice Chancellor and said, "Dear Vice Chancellor, if this is your specialist who pretends to be specialist, he called professor in celestial mechanics, and he makes such a big mistake, because ephemeris show that the distance change, as we said, and he claims it should not change. So either he doesn't know how to calculate properly this distance, so he cannot be professor in celestial mechanics, or he knows that the distances change, but he deliberately mislead the people. So this is the two things. The vice chancellor said, "Oh, he has right to have his own opinion." It is not opinion. It is a mistake, because this official ephemeris calculated with the multi-processor code, multi-body interaction, and they coincide with two observatories with 7 digits after comma. So this is precise data. These guys should be looking at this data before declaring that they will be the heating comes from the Earth, because they show that the distance change, and if distance change, if the boiler moves closer to you with the heating, obviously you have more heating here.
So why would they be motivated to go against the data like that? What's going on?
Oh, they didn't check the data. I don't know why they've been. Don't ask me what motivates people to do dishonest decision. I cannot tell you, and I don't want to have the lawsuit that I accuse someone. But this is the fact.
That's probably why
They did not use this data. Either they did not know, or they just deliberately ignored them.
So I want to understand more about this physical system. So as the sun moves closer to Earth in this 2,000 odd year cycle, there's also the decrease in solar activity. And the decrease in solar activity, does it decrease solar irradiance onto the Earth?
Of course. We come into the key point.
Okay.
If the sun is still closer to us, you see the summer is hotter, but when the solar activity becomes like it started decreasing now, because we're coming through the maximum cycle of 25, it will be decreasing next 5 years, coming to the minimum. This is where doesn't matter that the sun is close to us. This is where the heating from sun will be decreasing, and the temperature start decreasing. And if the temperature start decreasing on the Earth, it's evidence, absolutely undeniable evidence, that the heating we have on Earth comes only from the sun, because the sun is still close to us. The CO2, if they claim, which heats, still the same. But if we have, instead of heating, we start having cooling, then voila, we have the dominance of the sun.
Do you have a sense for how during the Maunder minimum, which was this cold period where harvests failed, summer didn't really come, it was very difficult on Earth during the Maunder minimum. Where was the position of the sun?
We are coming towards this period.
Where was the position of the sun relative to the position of the sun now during the Maunder minimum? Does that question make sense? If there's an oscillation in the distance between the Earth and the sun, and we right now have a close period.
During Maunder minimum, the sun was sitting in the focus of this, in the barycenter of the system. And now it started moving towards. So during Maunder minimum, it was not close. So we will have slightly warmer. I calculated, if you look at my book chapter, which I published in March 2021, in which I declared that every hour suggestion in the paper are correct. And we done everything correctly. And we calculated that the increase of the temperature will be by now by about 1.5%, by 1.5 degrees, 1.4. But decrease will be by 1 degree. So we have warmer winters during more than ground solar minimum, by 5.5 degrees warmer than in Maunder, because during Maunder, the sun was sitting in the barycenter. During our minimum, the sun moved towards us already for 300 years, or to some distance. So we will be slightly warmer, and our ground solar minimum will be lasting only for 3 cycles, not like in Maunder 6 cycles. So we have a little bit easier life, but you need to survive these 10, 15 years when it will be very cold. So we still need to survive.
Okay, so and then if we think about the motion of the sun away from the barycenter, right? So you're saying that right now the sun is in the barycenter, it has moved towards Earth, and so it's closer in these spring months. But is there a time period where it moves the opposite direction from the barycenter? So
it is in the 2000, after 2600, it start moving opposite direction and start moving back to the position like it was during Mount the minimum.
But you say that it's at the does it ever get farther away than the barycenter?
I think there's only 2 points it can occupy, right?
It can either be the barycenter.
It can either be in the center of the sun or outside of the sun. Those are the only 2 positions.
Yeah, it doesn't matter whether it goes further to the north. Definitely it will be until 2600. It moves towards the spring equinox position of the Earth. So we will be hitting more and more sun, but interrupted by a few grand solar minimum. So one grand solar minimum come in 2020, 2053. In another 330 years, it will be another grand solar minimum within 2375 to 415 will be another second grand solar minimum, when sun will be closer and the temperature will be reduced, but will be higher than even in this grand solar minimum for another half degree. So, and then will be 2600, and after 2600 the sun start moving back to the barycenter, to the temperature start decreasing. So this is what it was to expect.
I guess the question that I have is in relation to glaciations, where the Milankovitch cycle is the cycle that is generally used to model, to give cause for glaciations, right?
What cycle?
The Milankovitch cycle?
Milankovitch cycles. There's not one. There are 4 of them. So this is not Milankovitch. He did not mention. This is another cycle.
Yeah, no. I'm saying that glaciations, ice ages, are attributed to the Milankovitch cycles.
Yeah, but these are not Milankovitch. This is this is Halstatt cycle, and this is not related to the inclination of the Earth towards the ecliptics or its position towards the central solar system or to some other. These Milankovitch cycles, they have periods from 15,000 to 100,000 years through 43,000. We mentioned in our paper, which was retracted and which actually is most viewable paper whatever published, has 15,000 views already, and it keeps increasing with every day because obviously people realize if they retracted it, it's a very worthy paper. And so this is what will be happening. So this is a different cycle, which much shorter, 2 millennia period, but it's probably more important for us for living on Earth because it defines our usual oscillations. And to remind you that if you take 2,000 years from now to get global warming, in 500, 600 during Roman Empire, when Romans were in Great Britain, in Scotland, they had Roman baths when the stone was hit by sun, and they grew grapes in Scotland. So we have grape yards in Scotland grown by Romans. So it means that nearly 2,000 years ago, it was very hot in Great Britain. So it was this global warming of this Halstatt cycle, to which we're approaching from now to 2600. So if 500, 600 in Romans was hot, so 2500, 2600, this is what we will have, what Romans had before. And then it start moving back, like it moved to the Mount the minimum, it start cold again. So the only thing for us, we live maximum 100 years. For us, it's huge time. But from the point of view of planet, 2,000 years, it's a moment, instant. So this is what is happening.
Demystify Sci is hosting our very first conference. It is happening April 7th and 8th, 2024 in Austin, Texas, to coincide with the total solar eclipse that is passing through the area. Tickets are already on sale down in the description. If you go to the Eventbrite page, you will see a full list of the guests that we are going to have. It's going to include Pierre-Marie Robitaille, Ogi Ogas, David Ian Howe, Albert Nuremberg, John White from the Craig and Ford YouTube channel, maybe Steve Crothers. He's making noises about coming. But basically, you can go down there, you can purchase tickets. Conference tickets are about $200 right now, and that pays for the venue, that pays for the lodging and travel expenses for the guests, and for all the accoutrements of drinks and snacks and various setup for the conference itself so that it can be something that's really, really comfortable and really enjoyable. If you cannot afford $200 plus travel to Austin, that is fine. Right now we have $10 live stream tickets on sale, and if you buy them now, what you do is you directly help us put all of that money towards making the conference bigger, better, and more successful. So go to the Eventbrite link in the description and linked up here right now, and hopefully we will see you in Austin, Texas in 2024. Should we talk about solar physics some? Do you think that we've covered the climate stuff to depth, or what do you think?
Yeah, I'm really interested in your work on the helioseismicity, and I'm curious what you learned from that, and maybe you can talk about it a bit.
Oh, we now got contract with writing a book for Cambridge University Press, explaining how the sun quakes are occurring and how we observe them. So very soon you will have the whole book explaining it. At the moment I have a number of papers, I don't know, a few tens of something, but very soon we put this in one piece, big piece, book, 12 or 15 chapters, but we will explain this. I can speak about this, but we have much better last 5-10 years. We've done acceleration of particles in solar plasma, which actually very related to the fusion reaction, which in tokamaks with the trying. So we work with a physicist, and I do simulations with 3D particle in cell, which is top peak on the few universities, Princeton, few leading university did. And we did very nice simulations. So they definitely we on track understanding how to handle the fusion reaction, because again, the particles follow not only electric field, but they trapped in magnetic field, and this is very important thing. So this is different topic from what we are saying. It is not global, it is more local. But in many experiments in physicists, when they put in tokamaks, they had a lot of turbulence which disrupt whatever happens with this particle. So particles start accelerating, and suddenly instead of particles coming through, you have a lot of those waves, plasma waves, magnetic MMHD waves, and they couldn't understand where they come from. So what we recently published paper in 2021, which actually initiated this invitation to put a book, we explain how this turbulence is formed by those particles. So basically, as soon as we know where the turbulence come from, you know how to handle these particles to avoid this turbulence or suppress it. So this way, on this way, and we done this with my postdoc, who now works in Oxford. He moved, but the project was funded by US Air Force for 3 years, and we done a very good job for them. So, but this is not for general solar activities and energetic particles, which basically these particles which come to Earth, which you see behind me, aurora borealis. This is done by solar energetic particles. They all they precipitate through the poles to the lower latitudes, and they produce this borealis, all done by the sun. So I don't know who can suggest that sun has nothing to do with us. We live in his glowing light and glowing pictures and glowing particle rains coming to us, and we see them all the time.
What is the importance of the actual seismicity, though? What were some of the really exciting implications of discovering that the sun was ringing like a bell, and there was these little
the
droplets and so forth.
Helioseismology is the brilliant part of science, which started probably 30, 40 years ago. People discovered that the sun produced a lot of acoustic waves. The sun actually singing. They even recorded, if you go on the Stanford University website, they have sounds of the sun there. And our discovery of sunquake was done with the colleague who work at Stanford University. So I've been visiting them very frequently them at that time. So what these are global modes, P modes oscillations of the sun, which travel 5 minutes oscillation and others. So this was really big topic in beginning of 90s and 2000. But when I arrived, when we started, I was investigating flares. I was investigating, and I do in hydrodynamics of precipitation. So these particles injected somewhere on the top, and they go down, they hit the solar atmosphere, and not simply hit, they hit very heavily. They produce kind of hydrodynamic shock, like a hammer coming towards the solar surface. And if you have something very heavy coming towards the surface, and solar surface is like a density of the water, so it's the same kind of viscosity. So if something hits,
it looks like a liquid, right? It's very interesting.
It's like liquid. Yeah, this is the plasma, but
the plasma can, of course, be like liquid-like or gas-like. It's very interesting.
Yes, and then when this hammer hits the surface, we suspected that it should produce the ripples, like you see ripples when you throw the rock into the pond. You throw the rock and you see when the rock drop into the pond, ripples coming around from that position. So we thought we should see this on the solar surface. The only magnitude of this ripple, the height of the wave ripple, very, very high ripple. So you imagine how big should be this rock part going down. So I did simulations, I calculated all the hydrodynamic, I calculated the speed of these hydrodynamic shocks, predicted what kind of ripples we should observe, and then we got the new instrument. We had SOHO satellite flying in 1998, and they had the SOHO MDI instrument, which measured Helioseismic response, and its sensitivity was high enough to detect these 3-kilometer ripples, and we detected them, and we reported them on the American Geophysical Union meeting in May in 1998 in Boston. And I was the one who explaining to journalists the physics of it. And again, I reviewed, because I did simulation, I could explain and I explained them probably very well, because they pick up everywhere. It was simply understood, like if you have this rock thrown, instead of rock, you have this hydrodynamic shock produced by those particles traveling from the top. And we had exact calculations. My theory produced the exact calculation, which explained the speed of those ripples, the height, and all this stuff. And after that, we discovered about maybe another 200 sunquakes in cycle 23 and cycle 24, and now cycle 25. And this is what we adding now to the book, possibly. But what we managed to discover cycle, at the end of cycle 24, first time we discovered that ripples had the second bounce. So you have this wave coming down. What ripple is reflection of inner wave which comes on the surface. So what you thrown the rock, the wave came down under the surface, but it travels like a round trajectory, and then it comes to the surface. When it comes to the surface, it still keeps the momentum, so it pulls the surface up to the height of 3 kilometers, and then drops back and go again underground. And for cycle 24, we got the second bounce. So we found not only first ripple, but the second bounce ripple. We reported in the paper 2021. It's a beautiful observation, a beautiful result, and we managed to explain them. So this is what will come in the next book.
It's interesting that you talk about the surface of the sun, because a lot of mainstream astronomers treat the surface as a pseudo-surface, right? Like it's just some arbitrary density point at which, that the gas density is sufficient to produce a black body spectrum. But it does seem to interact like a real surface. Like it seems like a wild coincidence that you would have hydrodynamic.
The sphere is called the surface of the sun. This is the surface because when the density of plasma in photosphere is about 10 to 16, it acts like a surface. The above the atmosphere density of a chromosphere is 10 to 14, 10 to 10. When you get to 10 to 16, it looks like a surface, but it's still penetratable. It's still the gas, but it is a gas with the viscosity of water, the density of water. So this.
Why do you think that it's still a gas if it looks like water, acts like water, smells like water? If it smells like a liquid, sorry, not water, liquid. If it acts like a liquid, tastes like a liquid, behaves like a liquid.
Because we see from the spectrum that they have spectral lines confirming this is the gas. So
they have a black body spectrum, from what I understand,
which show the spectra of atoms. Not molecules, of atoms.
Well, they have a black body spectrum, right?
Molecules. Okay.
Oh, there's a black body spectrum at the photosphere, right? And all of the black bodies that we see on Earth are solids or liquids.
It is not a spectrum. It is assumption done, I don't know, in the 18th century or 19th century. Just forget it. We do real spectral measurements in wavelengths of particular elements. So we know how each element behaves in the photosphere. Specific part of solar physics, which investigate the photosphere's properties and densities and temperatures and variations. So this is why we know for sure it is the gas.
But hold on, the photosphere is one of the most perfect black bodies that we've seen, right? Like in terms of its spectroscopy.
No, forget about this black body. This black body comes from 19th century. We live in 21st century. No one.
But hold on, it does.
Hold on. I think let's move away from the black body idea and more that it has a continuous spectrum.
Sure, fine.
So, from what I understand, liquids and condensed matter gives a continuous spectrum, but gases give line spectra. And there's a theory that is about. I think that it's a statistical mechanics theory that uses the Compton equation, Compton scattering inside of the sun to justify how the individual photons bounce around for a million years inside of the sun to emerge to give this perfect continuous spectrum from which solar temperatures are derived. And the question is, if it has the density of liquid, and it has this continuous spectrum, which is...
Yes, density much deeper than liquid when it go into solar interior. And this is why dynamo wave propagate differently than other waves. So you need to learn a little bit about the sun beyond black body, because this is the simple school presentation. It doesn't work in real science. Just forget about it and stop using it because it is ridiculous.
But this is something that we've really been struggling with, because the idea of the continuous solar spectrum has bothered me for a while now, because it seems like the sun is very, very dense, and the theory goes that because of its density, a gas is able to create a continuous spectrum.
No, continuous spectrum created by different atoms. Even hydrogen atom can create continuous spectrum in Balmer continuum, Lyman continuum, and Paschen continuum. So you need to know a little bit of spectral analysis to understand. It doesn't come from the gas or whatever. It comes from atomic structure.
But it can't give a perfect black body like the sun.
Oh, there's no black body on the sun.
Well, it has a nearly perfect black body.
Forget about it and just don't bring it here, because I will not discuss it. It's complete nonsense. Nonsense.